So let's talk about tangent planes and linear approximations. So we could find the tangent plane to an implicitly given surface. And how do we implicitly give a surface? By taking a function of three variables, and here we are setting it equal to the constant 0, but in general you could get an implicitly defined surface with any constant, not necessarily 0. But here we'll just stick to 0, and of course all you could always redefine a function in order to give any constant, any level surface as a surface given by some function of three variables equal to 0. So that part's not so crucial. So let's just choose 0. And so this here gives you a surface, and now you want to find a tangent plane at a particular point on that surface. Okay? Well, since we could then take a path r of t that is on that level surface. So because it's on that level surface, it respects that relation there. Once you plug the path into the function of three variables, it equals 0. Why? Because of course the path is on the level surface. Now take the derivative. Okay, when you take the derivative by the chain rule, you get this guy here. And what does it tell you? That the gradient is orthogonal to tangents to the level surface, or said more informally, the gradient of a function of three variables is orthogonal to the level surface, right? The surface that we have given implicitly. So if you want a tangent plane, well, you're going to need a vector that is normal to your plane, right? And how do you do that? Well, we got a candidate there, the gradient, right? It's orthogonal to the level surface, so let's choose the normal vector as the gradient. Because it's orthogonal to the level surface, it will also be orthogonal to the tangent to the level surface. And what else? What's the other thing that we need to describe a plane? We need a vector, which is the normal vector, and number 2, a point. And here we could just take the point on the surface in which we're trying to compute the level, at which we're trying to compute the tangent plane. So here's a visualization that captures this concept. What you see in blue over there is the gradient, okay? So that's the gradient of a function of three variables at the point P naught, okay? And that gradient is orthogonal to this orange graph that you see. What is that orange graph? That is the level surface at where the function of three variables, capital F, equals 0. Okay? Now in green there is a curve that is on that level surface, and we could see the tangents that point tangential to the level surface, and we could change r of t. We could change its direction, right? As long as it stays on this level surface, then for any direction you choose that's along the level surface, the gradient will be orthogonal. So this will give us a way to compute the tangent plane, because we need a normal vector, and here we are. The tangent plane will look like the red plane that you see here. And for a tangent plane, you need a normal vector, and the gradient there provides, the gradient of the surface provides a normal vector of the tangent plane. So what then is the tangent plane? We saw it by that visualization. It's basically the plane that passes through a point P naught on the surface given implicitly by that relation there. And the gradient will of course point orthogonal to that level surface, and also orthogonal or normal to the tangent plane. So we need a normal vector for a plane, and here goes the gradient at ABC. So we're trying to find the tangent plane where? At the point ABC. So this is going to give us a normal vector at the point ABC, and this here is going to give us vectors that run along the tangent plane, and so we can get the tangent plane by this relation that the normal vector dot the vectors that run along the tangent plane are equal to 0. And just simplifying, we get this equation for the tangent plane. This is for a tangent plane for surfaces given implicitly. Okay, you just take the gradient and you could basically plug it into that equation there. So let's take a look at a concrete example. Here we have the function of 3 variables given by this, and setting it equal to 0, we get an ellipsoid, right? So if you move the 1 to the other side, you could clearly see that's an ellipsoid. And we want the equation of the plane tangent to the ellipsoid at this point here, okay? And you could definitely check that this point lives on the ellipsoid surface there. You could just take this x, y, and z and plug it in here, subtract 1, and you'll see that should equal 0, so that indeed it is on that surface. So we want two things for our tangent plane. We want a normal vector, and we're going to get it by the gradient at the point where we're trying to find the tangent plane. So we take the gradient, here's the gradient, plug in this value, this point here, and we get this value for the gradient, which we'll take as a normal vector. And for our point, we just use the point, so that's the second ingredient of a plane. And then just using this formula right here, plugging and chugging. So this here is f sub x 0, f sub x at the point 0, 4, 3/5, and it is 0. And likewise for f sub y and f sub z at this particular point. And so just a simple exercise there of using this equation, you get this relation here, and that describes the tangent plane to the ellipsoid at the point 0, 4, 3/5. So what you're seeing here is the tangent plane in red that we just computed for our function, okay, the ellipsoid. And you could see that it is indeed tangent to the surface, okay. Look at that, it's a plane and it's tangent to that surface. The gradient gave us the normal vector there, and the point that we're using to describe the plane is the point 0, 4, 3/5. So we have our normal vector, we have our point, and this gives us then the actual plane, okay, and it is indeed tangent to the ellipsoid.